Okay, folks, nice and easy lecture today, no horrible mathematics. Sit down and enjoy the show. I will introduce the symbolic algebra system that has been generating all the answers for your workshop problems. You will have noticed that what is there is a fairly strange syntax, and then the right answer mysteriously appears at the end of it. This is it. And the reason why we need to learn to use it is that the cost of a mistake to a chemist goes up quite steeply as you're progressing down your career. If you make a mistake here at the university, well, you get some points. So if I make a mistake, something goes seriously kaboom. And other colleagues at industrial installations really need to make sure things are right. I already told you that the only time I do mathematics by hand, by paper and pencil, is in these lectures and classes. In practice, life's too short and our time pressures are too strong to actually realistically have the time to do that by hand. You need to understand how it's done in principle, but ultimately we outsource this to symbolic algebra systems. Now, university has a site license for this. Just go and follow the instructions. It's not directly downloadable. You have to register with MathWorks, the company that makes it. The program has spent over 30 years in development. It's $1 billion company in the United States. And it incorporates, I would say, most of what scientists or engineers realistically require in terms of solving things. In particular, in my little corner of physics called spin dynamics, there are series, analytical series, that are not actually humanly computable. That is, although the final answers exist and they're small, the intermediate expressions are enormous, and megabytes or megabytes of formulas. It's actually not realistic to do it by a human, you have to do it by a machine, and this is why we do it. So you download it, you launch it, and you just type things into it, right? And on your keyboard, there are two enter buttons. One is the primary enter button that doesn't actually do much. It just gets the new line symbol in there. But there's the other little enter button that says evaluate. Press it, and you get 4. If you don't have the numerical pad on the laptops, it's Shift Enter. That will save you a considerable amount of time. It's the first thing everybody gets wrong when they install Mathematica. The second thing that we need to get out before we begin with the actual thing is there are 3 different equal signs in Mathematica. The usual equal, like A equals 2, that's an immediate assignment, right? It says, okay, put A equal to 2, and it does it. And the next time you request A, it will tell us 2. The other equal sign is what's called a delayed assignment. So, for example, like that A of x variable is sign x. It tells you that what you should do, in this case it failed because we've already assigned A, so let's just assign B. Right? This is a delayed assignment which says assign but don't evaluate. So every time we actually request B with any specific number, like B of 3, it will return a sign of 3. And you can see it doesn't actually compute it unless we specifically insist on the numerical answer, in which case the numerical answer is provided. So it keeps things analytical as much as it can. So there's the immediate assignment and there's a delayed assignment. In the situation when the right-hand side is very expensive, this matters because it's not immediately computed. And then the last type of assignment is called a logical check. It simply asks a question of whether something is equal to something else. Right? So double equal sign says, is this equal? The answer is true in this case. Or is A equal to 3? Well, apparently not. So these 3 different equal signs, they will make an appearance in what we have later. Okay, so this goes through the list of the various things that Mathematica can do. So let's just delete all console output. And then we'll take a look at what we can do. So starting with the basic course, you will all have chemistry maths. We will all have the need to plot various things. separately, simultaneously, and so on. So the command is just plot, and if you click on it and you press F1, the standard button for help, it brings up the documentation, and the documentation is huge. And you click on the scope, and there are various ways of labeling and legends there, various bounding lines. There's over 100 different options of the filling style for the plotting function, multiple applications, lots of examples, and such like. So it provides a fantastic variety of various plotting opportunities. This thing is twice as old as you are in terms of its development times that went into it. It really went quite sophisticated. And as you can see, the documentation is enormous. When I was starting my undergrad in 1998, there was a book called the Mathematica book, and even at the time it was this. It was really, you use that thing if you hate trees, and if it falls on your shelf, it's a health hazard. So they stopped publishing it because the thing became just too big to realistically print, but the electronic manual is still online. Okay, so if we press that, right, it simply says plot sine x for x from 0 to 6 pi, and this is it. And then this pi, we use the text syntax for it. We can actually use the Greek syntax as well. Pi letter here, 10 pi. Then if you want to plot things simultaneously, like sine 1x, sine 2x, sine 3x for some x, and here's an option says, okay, use expressions as legends. It will plot you all three functions, and it will create the legend. It can label the axis, it can put it as a box plot, and so on. You can see immediately that even by the visual appearance, this is way neater and way easier to use than Microsoft Excel. And I would actually discourage you from ever using Excel because it's an interesting psychological problem. Your professoriate has seen so many horribly written student submissions done in Excel that Excel became associated with horrible student submissions. So it's a bit of a stereotype by now. So try using something else when you are doing the plotting. Otherwise, you're kind of instantly prejudiced the moment you see it. Various other options, like for example, fill in the area between the curve number 1 and curve number 2, where curve number 1 is this sine and curve number 2 is that sine, and it will do it. Various other options exist. There's a three-dimensional plot thing for functions of two variables called plot 3D. And so if it's a sine of x plus y squared for a rectangle for x from -3 to 3 and y from -2 to 2, it produces a three-dimensional plot, which you can then actually rotate around. And various other things like x power 4, and then it produces something really horrible. And as you can see, the system is not perfect, right? In this case, it undersampled the function. You can specify the number of sampling points in the surface, and then it will digitize it correctly and produce decent smooth power. So again, plot 3D with the documentation site contains all sorts of weird and wonderful types of plotting and a great number of different options. Okay, now some plots are trajectories, that is your x and the y coordinate of your particle will be independent functions. For example, time. In this case, the x coordinate changes the sine of time, and the y coordinate is sine twice the time. If we plot that, we get the simplest version of what's called a Lissajous figure. If we put some other numbers into here, like 7, 11, then we'll get something a little more complicated. But this is the trajectory of a particle in a situation when the two coordinates are just two independent different functions of time. Or we can make this a log, or something else. Log S1, so it doesn't go haywire at 0. So this type of trajectory where the x coordinate is oscillatory, but the y coordinate is a logarithm. Then in 3 dimensions. So for example, if you have your x changing as a sine and your y changing as a cosine, that's a rotation. But then if your z changes linearly, it will be a spiral. in 3 dimensions. And so sine t, cosine t, and t over 10, to slow it down a little bit, that's your spiral in 3 dimensions. So almost any type, including various implicit and complicated parametric versions of that, like plotting patches of different surfaces in various ways, read the manual, you will find it. In many cases, plotting surfaces like this is not a good idea because it's actually pretty hard to perceive this visually or quantify. In various places like radio astronomy, actually the more popular way of plotting two-dimensional functions is like this, where this is y, this is x, and the intensity on the z is mapped into color. So blue is low intensity, white is high intensity. You can choose different color palettes in the options. And this tends to be easier to perceive, and actually this corresponds rather well to a lot of imaging, because an image can be interpreted as probability density or color density, in which case what was a two-dimensional image becomes a three-dimensional surface, but it is easy to perceive it in terms of colored light. Or you can use it with contours, so it's essentially the same colored picture, but these curves represent the manifolds on which the function has exactly the same value. So each of these curves, they're called isolines, which have surfaces in 3 dimensions, are just the lines or surfaces of constant form of that function, so contour plot does that. When you go to multiple integrals in your second semester, if you go and choose the option module mass, in many cases the integration region in 2 dimensions is not just a trivial square, it may be complicated, some curved region, and this is the function that plots those regions. It says, okay, plot me everything on the xy plane where x squared plus y cubed is less than 2. So for some points on the 2-dimensional plane, this is going to be true. For other points, this is going to be false. And if we now plot that, it's x from -2 to 2, it's y from -2 to 2. The blue shaded area is when this inequality is true, and the white is when it's not true. So it's the region plot. You can nest complicated region plots, like plot me a region where x is greater than 1 and x is less than 2 and y is greater than x squared and y is less than x plus 9. So it's not entirely clear whether points even exist that might satisfy that condition, and it's clearly something very complicated. So if we look at it, we say between 2 vertical lines, a quadratic curve at the bottom and a linear curve around, and if we specify something that's not actually realistically even feasible, then we will get an empty plot at the end, because such points do not exist within the intervals that we specified. So this essentially saves you time, right? Trying manually to visualize what is the set of points that satisfy these weird inequalities. It'll take a while, and if you just type it into the machine algebra system, it produces you the answer instantly. The same can be done in 3 dimensions. I mean, this is simply not humanly possible. So plot us the area in 3D space for which x squared plus y squared minus z squared is a positive number. And then you get this area, some kind of cone/paraboloid, and it's cut off by some intervals we have specified. So these are not things that are easily doable. And I've uploaded this to Blackboard, so there's a practice area, just type whatever it is that you like, and it will plot it. It does 3-dimensional volumetric plots. I don't actually think it's the latest version of Mathematica that did that. Volumetric plotting. Let's see what we got in there. Raster 3D. So that does things like this transparency in 3 dimensions. So neat examples. Image 3D, that's interesting. There we go. So you can plot bits and pieces of internal combustion engines and so on. Some kind of diffusing process, some MRI imaging, it doesn't need to rotate in real time. Okay, so on to slightly more interesting things. One thing that you will often need is simplify symbolic expressions. You look at some horrible crocodile and you kind of get the idea that maybe it is possible to simplify this. And the command is just called simplify, so that's your sine squared plus cosine squared. You simplify, it simplifies to it. In the interesting case, for example, if we tell it to simplify x squared y squared, it actually wouldn't do it. So we just put it separately in here. It will keep it that way. You as students would actually be tempted to simplify, but Mathematica understands that x could be a complex number or a negative number, in which case there's sign ambiguity in here. And so it cannot actually simplify because it doesn't simplify. A simplified expression would lose some combinations of signs. So it knows that and it keeps it unevaluated. However, you can say, assuming that x is positive and y is negative, then this simplification will produce something. So it's actually minus xy in this case. Or if both are positive, then this is just plus x. So it corresponds to all various possibilities. So in some cases it would decline to simplify things because you haven't given sufficient information for the simplification to be possible. Expanding trigonometric expressions, so into the standard products, or if you have a product, reducing it back into individual trigonometric functions, converting cosines and sines into complex exponentials, Euler's formula, converting complex exponentials back into sines and cosines x to the 3. There you go. Expanding complex numbers into real and imaginary part. That's a function, and if you put all the RE's and E's in there, it expands it out like that. Factoring enormous polynomial expressions, the things that you could never quite remember from the school textbook, even though they told you to, or expanding enormous fractions. And again, if we put power 100 in here, it wouldn't even blink. So that it does. And it wouldn't blink on a great number of things. But if you, for example, do that, you say, okay, give me I to 10,000 decimal places, and that is a big piece of time. And if you ask it for 10 million decimal places, it will print them. It will take a while to print, but it doesn't. So it's actually an arbitrary precision library underneath, which is seriously sophisticated. Solving equations, right? Things you'd rather not do by hand because, for goodness sake, when this is going and right now make quadratic equations, I have to stop anyway. There you go. So x is minus 4 and x is 3 halves. If they have complex solutions will be provided at the end. If solutions do not exist, it will tell you so. It will solve equations of powers greater than 2, and you will have these horrible radical expressions. Actually, the theory says that I think these have expressions in radicals only for powers less than 5, I think. So if we put power 6, it probably wouldn't give us. So it returns a generalized object called the root of this expression because it understands that the explicit formula might not exist. So it is rather sophisticated. Systems of linear equations just specifies the first equation. Notice the logical equality here that we are not assigning, we are telling Mathematica that this is equal. So you should use the double equal sign in all these equations solvers. So solve this system of linear equations for x and y. There you go. 3 equations for 3 unknowns. There you go. Right, non-linear equations indicate solutions exist. They will come out. If they're complex, they will be complex. And here's some thermodynamics for you. You must have seen this by now, the Gibbs free energy and the enthalpy.
Okay, so these are expressed for some other functions of state. We have two equations. We can tell Mathematica to combine them in such a way as to eliminate them from the expression. There we go. It has combined them and eliminated H. There's now one equation that doesn't contain H. Simply, it solved that for H and then substituted it there and simplified. There we go. So almost anything you would realistically have will be soluble either analytically or numerically. There will be situations where analytical solver fails. We ask it for something like x equals to x. You know well that this doesn't have any closed form answers. It will give some strange thing called product log, which can be viewed as an elementary function, but it really isn't. In which case, nsolve is a numerical solver for that, using, let's say, Newton-Raphson that we've been using. And remember the syntax, it probably will work. There you go. So it produced some kind of complex solution for this. We can probably ask it for a real solution, in which case solution doesn't exist, and so on. So you can have plenty of practice with that. And at your laboratory practicals, for example, to test that you've done some calculation correctly, this is really quite useful. Differentiation, so just a standard symbol for the derivative. You've got some really complicated function. In this case, it will be a triple product rule followed by a chain rule for this. So if we do not tell it to simplify that, it will be, actually not do that. If we ask it to simplify, it might, simplify a little bit in the end. X, sine, log, so really horrible series of chain rules and so on. Partial derivative with respect to x of some variable. There's an expression that depends on 3 variables. There we go. And even in complex arithmetic, we get things really hyperbolic sine in this case, if you do that. So we can ask it to differentiate something really horrible. So derivative with respect to x of, for example, x to the x to the x. Now, doing that by hand is interesting. We wouldn't even know where to begin in many cases, but there you go, that's the big one. So differentiation is algorithmic. Any sufficiently well-behaved function will have a derivative. Integration, something that you are doing now. You know, this is easily integrated by substitution. If you put 1 with sin x equals y, but Mathematica just returns that instantly, never prints the constants, don't forget them. You know, seriously difficult stuff like higher powers of trigonometry, it still produces it, that's a definite integral. And then various other things in there. So we can ask it to integrate something that is quite complicated, to see perhaps a situation in which it might not be able to integrate. So let's say the exponential of cosine of the log of x. Now this, and perhaps just for Woody measure, let's throw some polynomial expression into that. So I would be very surprised if this is analytical, but it might just be, see, it left it unevaluated, so it's not, it doesn't exist in the closed form. However, if we do this and ask for a definite integral, we'd better use an explicit integrate that expression with respect to x from 1 to 2. That's unlikely to work, although it will put some reasonable effort into it, but it is not likely that it will produce the answer. So you can see it's still right, and it returns the integral unevaluated. In which case, n integrate, the subject of the next lecture, numerical integration. It will slice the function into tiny little slices. Remember the Riemann sums that I've introduced. in one of the lectures. Some of the slices take the limit to a point when the integral is accurate to machine precision and as your answer. So even if you don't have an analytical answer, you can still have a numerical answer, which in many cases will actually obtain. Differential equations. D solve f prime of t equals kf of t, standard chemical kinetics. That's your exponential with a constant because we are asking for a general solution. If we want a particular solution, we tell it, okay, f at 0 is equal to 1. Notice the double equal assignment, in which case a particular solution will be returned. In this case, of second order chemical kinetics. You have seen this many times. Systems of equations, dA by dt, in a reversible chemical reaction. A prime is minus k1a plus k2b. Physical chemists have tortured you sufficiently with this by now. That's your solution, and as you can see, it's actually pretty complicated in the general case. And if you actually have specific initial conditions in there, like time 0, a was 1 and b was 0, it's simplified. And so you have these as the usual rising and decaying exponential of the reversible first order kinetics. It can solve partial differential equations. That's the subject of the next semester of this course. In this case, the diffusion equation, and there we go. It has it. So again, there's a practice area here. We can ask it to solve something really complicated, like for example, an equation which is not first order, but perhaps third order. Occasionally, you can see that in mechanics, and you can see it returns a linear combination of exponentials with 3 indeterminate coefficients. So the equations that we didn't even consider in this course, this thing can solve, and either analytically or numerically, the analytical solution doesn't exist. Now, matrices and vectors, to a limited extent, have been introduced at school. We will see more of them when we go to quantum mechanics. Quantum mechanics is all about matrices, particularly spin physics and electronic structure theory. So you can supply lists of variables, or you can treat those lists as matrices. If you tell it to put it in matrix form, basic operations like transpose, multiplication. So you take this matrix and multiply it by that matrix. So if we create like a random integer matrices and ask them to multiply them together, notice that the multiplication for matrices is not a star, it's a dot. If you use a star, it will multiply matrices element by element rather than in the correct way. So I'm not going into details of that because we haven't yet properly introduced matrix vector algebra, but sooner or later you will get there. And it can calculate various things, like matrix inverse is a truly horrible operation if you're doing it by hand. So many obscure stages. It does it in milliseconds. Things like matrix exponentials, it's a central object in independent quantum mechanics. So the evolution operator is an exponential with Hamiltonian. So all of that is done. So any operation with any matrices or vectors, diagonalization, determinants, and so on, is easily getting computed. So we can take this matrix and ask it to calculate the determinant of it, and it will do it typically. That's your determinant. And actually, in this case, it didn't simplify it, so we can say, tell us the determinant, and then simplify. And that's interesting also. So it has recognized the fact that this all the signs are actually simplifiable. Taylor series, remember the trouble we had with differentiating it multiple times, then detecting the pattern, and so on. That's the Taylor series for x log x to 15 terms. So in the time that it took me to press the button, it differentiated the function 15 times and produced the series. We can put something else in here, that's cosine x over x. So this never simplifies, it will always differentiate to something horrible. And as you can see, the series will generate pretty quickly. And it's pretty clear here that the series for this function is converging very slowly because even the 15th coefficient is actually quite large, quite large, not sufficiently small. But in this case, you can see the denominator is growing really fast. So this series will be better converging than that series, and so on. It will do Taylor series with respect to multiple variables, something we didn't even consider for lack of time. So if you ask it for a series up to third order in x and up to third order in y, it will produce a function. And if we drop the various residuals, this is for standard form. No, normal form. There we go. And if we now plot this function next to the series that we have using plot 3D, that horrible function with respect to x from -1 to 1 and y from -1 to 1. That's your three-dimensional plot. And if we ask it to plot the original function as well, chances are it will be pretty close because it's a Taylor approximation after all. So you can see the two surfaces are very nearly coincident. There's like a tiny little bit of a deviation. So this two-dimensional Taylor series to third order is a pretty decent approximation to the surface of the original function. Propagation of uncertainties. So this, I would not go into the details of how this strange expression works, but you can program such things in Mathematica. It automatically differentiates squares and puts it under that root. You've all been doing that, so if we declare that function, notice the delayed assignment sign here. We are actually asking it to hold off evaluation until it knows more. And then that's our calculation of pressure. It's the problem from the workshop, nRT over V. nRT and V, these are the values, and those are the four uncertainties. The pressure is this with the uncertainty of that. So again, an instant calculation. Applications to chemistry, well, some are sort of silly. You can ask it to tell you a joke, and it will do it. For some reason, it already pre-evaluated it. So tell me another chemistry joke, so one I haven't yet heard. Okay, connecting to the database. Yeah, always. Let's see. Set the query to MathWorks server, which has some limited artificial intelligence capabilities, and hopefully it will return us some answer. There we go. Well, no, apparently it just gave us the definition, but okay, so tell me a chemistry joke. Okay, why did the atom rush to the lost and found? It was positive, but was missing an electron. So as bad as Christmas crackers, right? But any jokes about sodium? Nah. Okay, so the melting point of tungsten, it has a database of all the basic physical chemistry. Entropy of toluene at 350, so it will pull the standard entropy, pull the heat capacity, do the integral, and return you the standard entropy of toluene in joules per kilogram, for some reason Kelvin. Various van der Waals things, like things we'd rather not solve if we want to solve the van der Waals equation for pressure. This is it. Lennard-Jones potential, something that you've already seen. This is where all the plots are coming from in my lecture handouts. So that's the energy minimum, and this is the collision wall. Reaction kinetics, right? We are solving a bunch of differential equations, and then we are plotting the solution for specific values of the kinetic rate constants. So in the case when the two constants are equal, the concentrations equalize over time. And if the forward rate is twice as fast as the backward rate, there will be more product than there was the reactant in that equilibrium. So you can do some chemical kinetics modeling. Some really complicated chain reaction in this case. Okay. There we go. So with the reaction intermediate, so the initial substance drops, intermediate accumulates, but then gets converted into product, and the product rises quadratically rather than linearly, and eventually starts dominating the reaction. You can sort of abuse the computer a little bit here. You can say, okay, hello, well, hello, human. There's something called the Batman function in computing. It's a piecewise defined function that looks like a Batman. I think that's quite a lot of calculating. So if you ask it for Batman curve, it produces you the Batman curve. Or if we try and remove that, say draw me a dog, it might do it. Come on, draw me a dog. It used to do it. It changes over time what it does because the developers are working on it. Okay, but I think the rest of the examples, right? If you're not being polite, it will ask you what your mother would say. It does have some limited cultural knowledge. So speed of unladen swallow is 25 miles an hour. 1975, film Monty Python and the Holy Grail. The meaning of life is obviously 42. Then that's the definition of love that I use. It's from Seneca, but if you ask for the definitions that it has, strong positive emotion, sexual desire and attraction, score of 0 in tennis or squash. Presumably, words that rhyme with duck, the obvious one is missing from the list. Scrabble in here and so on. So acetyl, acetone, you probably wouldn't find in the standard Scrabble dictionary. And so on and so forth. So on a more sort of serious side, I really like those jokes. They're actually pretty good. Did you hear oxygen and magnesium get together? Oh my God. It's not bad, right? Okay. Right. So that is the system. It has things like least squares fitting. It has minimization and maximization. So let's go, for example, maximize something that clearly has a maximum, like 1 minus x squared with respect to x. X equals 0, in this case, we say x minus 5, so that shifts the minimum to 5 as your x, and that's the value. If we make this a bit more complicated, we square it again to make sure that that is an interesting function. Then the maximum is actually at minus infinity, and it's equal to infinity. There's a numerical version of this, there's a minimize. There are various ways of solving, for example, inequalities. If we go back to these solvers that we had, where it produced multiple solutions. So there you go. So solve this. It's 1, 2, 3, 4 different solutions. But we can say solve as that, but only for situations when x is greater than 0, only 2 solutions are left. Or only for situations when x is greater than y, and other 2 solutions are produced. So play with it as much as you can. It would occasionally produce answers in terms of functions even I haven't heard about. It's a really sophisticated system. Occasionally it will crash your computer because it will in turn run out of memory, but overall it's pretty good. Though one word of advice, don't try to program in it like any kind of extended for loops or anything. Mathematica's programming syntax is horrendously bad. By the time you need to write an actual program with better original code, because it's designed for lengthy code, Mathematica is really quite horrible. Okay, so the next lecture will be about the numerical methods and a little bit of applications, artificial neural networks. I am again away in Singapore, but I think Maria will read the numerical methods lecture, and I'll re-record the artificial neural networks one. And I'll see you after Christmas. Any questions?